Welcome, everyone, to section 1.4. And I have some good news and I have some bad news. So we're going to start with the bad news. The bad news is that this textbook is a little silly, and I appreciate that it's free and you don't have to pay for it. That's what free means. Um, I appreciate that it's free, but it's kind of silly sometimes. And that leads me to the good news is there's not a lot new in this section. So the videos hopefully should be pretty short. We'll introduce some topics, but most of this section is just going to be, let's do application problems. That's most of the section, just application problems, application problems, application problems. And they're all similar, but they're not all the same. So they will require different strategies. And I'm trying to have a long selected homework problems video for this section to give you a lot of extra examples to help things out. But as is always going to be the case, I can't cover everything. I don't want to cover everything because I want you to have to apply some of what we're doing and not just copy things down. And I want you to ask me for help, ask your fellow students for help, work together, and yeah, hopefully give you a good opportunity to learn something and do some cool stuff. So we're going to start with an introduction. Basically, in this section, again, there's not that much new, mostly applications. I kind of already said that. And then in the third video, we talk about even and odd functions some more, which doesn't have any directly related. It's going to be a lot more useful for later. So the third video here will be more useful in the future and slightly useful now. So let's get started with the net change theorem. And before we do that, let's just do one example, one little review. Again, a reminder on antiderivatives, definite integrals, and how we can solve some problems in a variety of different ways. In this first example, you should already be able to do this, but let's evaluate the integral, the definite integral from 1 to 4 of the square root of t times 1 plus t dt. Okay, and the important thing here is we need to take the antiderivative so we can use a fundamental theorem of calculus and evaluate a definite integral. But it's hard to take the antiderivative of this. We don't really have a product rule for antiderivatives. There is something that's basically that, but we don't call it that, and we haven't talked about it yet. So what we're going to do is, since these are both rational, well, they have rational exponents, we'll just combine them, distribute. So if we distribute, what we're going to get, again, thinking about the square root of t as t raised to the 1/2 power. And if we distribute this, we're going to get the integral from 1 to 4 of t to the 1/2 power plus t to the 3/2 power. Because again, we can think of this as t to the 1st power right here. And then we're integrating dt. And now I just want to make one more comment that there's kind of two ways of going about this next step. So in fact, I'm going to do both of the ways. We'll do a blue way, we'll do a green way. So the blue way is, I think, what is very common in a lot of calculus classes. And what that is to just take the antiderivative, use the power rule. So we add an exponent. We add 1 to 1/2, we get 1.5 or 3/2, and then divide by that exponent, that new exponent, dividing by 3/2, same as multiplying by 2/3, and then do the same thing with the other one. And then this is shorthand to say, okay, that's the antiderivative. We need to evaluate it at 1, evaluate it at 4, and take the difference between the two. And we just plug it in directly in this first blue method, the common way of doing this. If we do that, the first thing becomes 2/3 times we get 4 to the 3/2 plus 2/5 times 4 to the 5/2. And then we subtract out what happens when we plug in 1. And really this is equivalent to the other method, but it's just kind of a little messier, but a little quicker. And we'll show that second green method right after this. So once we get here, we just evaluate and simplify. Lots of places to make calculator errors right here. Okay. This is 2/3 times the square root of 4, right? That's what that 2 in the denominator. Square root of 4 is 2. 2 cubed is 8. plus 2/5 square root of 4 is 2. 2 to the 5th is 32. And then 1 to any exponent, 1 to any real number is 1 still. So the second one will just be 2/3 plus 2/5. And you could go along simplifying this all out and get to the right answer. All right, and once you simplify it all out, you should get to 256 over 15. And 256 is an exponent of 2, so you know it doesn't cancel with the 15, and that this is fully simplified. Okay, so the other way of doing this would just be to use a slightly different notation. Is once you get to here, instead of writing it like that, I'll show the other way in green, is you could write it as f of 4 minus f of 1. And this is a lot of times easier to not make mistakes, which algebra mistakes I always make, students always make. We all always make algebra mistakes, which is why it's so important to check our answers. And then again, where f of x is that antiderivative, which is 2/3 t to the 3/2 plus 2/5 t to the 5/2. And then again, you just go down. It becomes very similar from here. You calculate what is f of 4. And so we calculated what f of 4 was right here. Could simplify it a little bit. That's going to be like 80 plus 192. 80 plus 192 is 272, I believe, over 15. And you could do the same thing for f of 1, and then you just subtract them. And it's a little easier to not make mistakes on this. Although now I'm doubting myself. Is f of 4 really 272 over 15? Hey, it is great. And you could do the same thing for f of 1 and then take the difference that way. So that's another way of doing it out. You kind of decide, do you prefer this method or this method? Again, I think the green way is really sometimes a little more stuff, usually more steps, but it oftentimes is less messy than this. Your choice. And that's mostly one of the reasons I wanted to do this problem, is just to remind you that there are different ways of approaching these problems and putting them in your notes or when you do them yourself. Okay. So next problem is in the next video. But before we get there, we want to introduce a new theorem. Okay. And that's called the net change theorem. The quotation marks will become obvious soon. So basically, there are some assumptions that you can make, but basically, this is just relationship between a derivative of a function, the area under the curve, and the net change. And it says that f of b is equal to f of a plus the integral from a to b of f prime of x dx. That's the net change theorem. That, again, under certain differentiability and integrability assumptions, this is true. Now, the reason why I have quotation marks is look what happens if I subtract f of a from both sides. What if I subtract this thing over? Well, if I subtract that thing over, we get f of b minus f of a is equal to the integral from a to b of f prime of x dx, which is literally the fundamental theorem of calculus part 2. Okay, so we already did this in the last video. Now, sometimes this form will be more useful, especially when we do like initial value problems and stuff like that. But really, it's the exact same theorem. Okay, so this basically says the net change of f is just the area under the curve of its derivative or rate of change. And that's what we're doing in this section. A bunch of applications of, okay, what are some different quantities that we can look at where we're interested in the rate of change, the net change, and we might already have the rate of change or slope or derivative. And we're basically just using the fundamental theorem of calculus, the whole section, okay? So not a lot new, just maybe some different phrasings and a lot of application problems. And that's where we're going from here. So let me know if you have any questions. Otherwise, feel free to start some problems, or if you want some examples, the next video is for you.